When it comes to pure water does not only contain water molecules, it does contain some H plus ions and it contains OH minus ions. This is why water can behave as a bronzed acid or a bronzed base. See in the examples up there, we gave an example where water behaves as a bronzed acid because it is reacting with a base. And here, water behaves as a bronzed base because it was reacting with an acid. So, water has a double role, either an acid or it's a base. And the concentration of the H plus and the OH minus in the solution for the pure water, they are actually the same. They have equal concentration in there. So water in the reactants, this is a pure water. So if you have a pure water liquid, pure water exists in solution. It ionizes in the solution, and it contains H3O plus aqueous ions, and it contains an OH minus aqueous ions. Okay, the concentration of the OH minus and the H plus is going to be the same. Both of these, they have the same number of moles and they contain the same concentration, which is 1 times 10 to the minus 7 moles per liter. So this is why we say water is a neutral, because the concentration of the H3O plus and the OH minus, they are equal. They are the same. So if we are looking at pure water is neutral, and the pure water is a neutral again because it is present in a specific constant concentration. So always the concentration of pure water is 1 times 10 to the negative 7 molar. This is the concentration of the pure water. This means that the concentration of the ions in the water, which is H plus, is the same as the concentration of the OH minus. And by the way, this is how we represent the concentration. So we put the ion in the brackets, and this is considered to be the concentration. So the concentration of the H plus ions is the same thing as the concentration of the OH minus ion for pure water, and these have the constant concentration, which is 1.0 times 10 to the minus 7 molar. Okay, so always pure water has a constant concentration, and it is 1 times 10 to the negative 7. It does have a constant concentration because the concentration of the H plus ions are the same as the concentration of the OH minus ions. So if I look at this equilibrium reaction, this is an equilibrium reaction. You do have an equilibrium arrow in there. So if I look at this equilibrium reaction and I want to go ahead and write down the equilibrium expression, K equilibrium. So now K equilibrium, we already know from the last chapter that it's the concentration of the products divided by that of the reactants. So you look at your products, and your products are the H3O plus and the OH minus. So this is the concentration of each one of those. They don't have a coefficient. So it's the concentration of H3O plus multiplied by the concentration of the OH minus in the solution divided by the concentration of the water. You do have to water, right? So it's the concentration of this multiplied by the concentration of that. Since these two are the same, so I'm just going to make it squared. So what's going to be the concentration of the water squared? Now, the concentration of water is constant. So water has a concentration that is always constant. So it's the water concentration is always constant because water has a known amount of moles of H plus and OH minus. They have known amount of moles of 1.1 times 10 to the minus 7 moles of H plus and 1 times 10 to the minus 7 moles of OH minus in there, and it's moles per liter. So each one of these ions is equal to a concentration of 1 times 10 to the minus 7 molar. Molar means moles per liter. Okay, so because water has a concentration that is constant, I'm just going to go ahead and make a relationship between the equilibrium of the water and the concentration of H plus and the OH minus. So I would say, okay, so now K equilibrium, I'm going to call this a constant K, okay? So this is the water concentration. So let's assume that the water has a constant concentration, which is K. So I would say now K equilibrium times K, because both are going to be constant now, that is equal to the concentration of H3O plus multiplied by the concentration of the OH minus. And then I would say, okay, K equilibrium and K, since both of those are constant, I'm just going to give them, because this is the dissociation of the water equation, as you can see here. This is the dissociation of the water equation. This is the equilibrium of the water. So I would say, okay, those two are going to represent K water. So this is K water. And the K water is the ion product of water. So K water is the ion product of water. So I would say, okay, K water is equal now, this is the relationship, it's equal to the concentration of H3O plus multiplied by the concentration of the OH minus. Or I can say K water is equal to the concentration of H plus. H3O plus and H plus are the same. Okay, this is the acid component of the water when it dissociates, and the basic component, which is the OH minus of the water that is dissociating. So this is going to be my first equation for the equilibrium constant of the dissociation of the water. Now, if I want a value for Kw, because it's known, the concentration of the H plus is the same thing as the concentration of the OH minus, right? Because H plus is 1 times 10 to the minus 7, and same thing for the OH minus. So I can get actually a concentration for, or a value for Kw, which is the equilibrium of the water. So Kw is the concentration of H plus multiplied by the concentration of the OH minus, and that is equal 1.0 times 10 to the minus 7 multiplied by 1.0 times 10 to the minus 7. It's like 1.0 times 10 to the minus 7 squared, okay? So it's equal to 1.0 times 10 to the minus 14. This is Kw. So Kw is a well-known value, which is 1 times 10 to the minus 14 in there. So in the equation over here, I'm just going to add it. So that is equal to 1.0 times 10 to the minus 14. Okay, that is minus 14 over there. So minus 14, and this is the equation, and this is the relationship between the concentration of the H plus and the concentration of the OH minus. So if you're given the concentration of H plus, when do you use this equation? If you're given the concentration of H plus, you can calculate the concentration of the OH minus, because Kw is known. This is the value of Kw. You know H plus, you can calculate the OH minus, and vice versa. If you know OH minus, you can calculate H plus as well. Okay, so the value of Kw is always any solute that is dissolved in water. You do have a Kw in there, and the Kw is 1 times 10 to the minus 14. Now, if you look at the pH scale is distributed between 0 and 14. This is the pH scale, where when you go more towards the 14, this is going to be basic. And the closest to the 14 is, the more basic your solution is. The closest to the 7, this is going to be less basic your solution is. And then pH equal to 7, that is a neutral. Below 7, now this is going to be your acidic region. So if you are 0 or between 0 and probably 1, this is going to be more acidic. And as you go more towards the 7, that is going to be less acidic. Okay, so that region over here, it's going to be less acidic. So the closer it is to the 0, the more acidic your solution is. This is less acidic. And the closest is to the 14, the more basic your solution is, and the closest it is to the 7, the less basic it is. Okay, so when the pH increases, your solution is going to be more basic, and when your pH decreases, then your solution is going to be more acidic. An acidic solution is a solution, since it is acidic, it should have a higher concentration of H3O plus ions, more than OH minus ions. This is why we call the solution acidic, and its pH is less than 7. A basic solution, another name for it, alkaline solution. So this is a basic solution, and the basic solution is whenever it has more OH minus ions than H plus, then I would know my solution is going to be basic and its pH is going to be more than 7. The closer it is to the 14, the more basic it is. So this is the relationship between the pH and the concentration. So we have two relationships here. pH is equal minus log. This is log base 10. Okay? So minus log in your calculator is log base 10. So it's going to be a minus log concentration of H plus. And the POH, that is equal to minus log concentration of OH minus. Why do I need those? If I'm given the concentration of H plus, I can put it in this equation and get pH. Same thing for the OH minus, I can put it in this equation and get the POH. Also from this, I can relate this into the concentration of H plus. So concentration of H plus is 10 to the power minus pH. Knowing the POH, you can directly calculate the concentration of the OH minus. Knowing the pH, you can calculate the concentration of H plus. Let's have an example. Calculate the molar concentration. This is the regular concentration in moles per liter. This is why it's called molar. So molar concentration of the OH minus. So what they need over here is the concentration of the OH minus. This is what they need. They gave us the concentration of H3O plus, which is the concentration of H plus, and they want the concentration of the base. They gave the concentration of the acid, they want that of the base. That's the first part of the question in there. So I know that there is a relationship between Kw, the concentration of the acid, which is H3O plus, and the concentration of the base, which is the OH minus. I already know Kw. I already have the value of Kw. Kw is equal to 10 times, actually 1 times 10 to the minus 14. So it's 1.0 times 10 to the minus 14. This is the concentration of Kw. I already know the concentration of H3O plus, so I can simply calculate the concentration of the OH minus. Let's put an equation over here for the OH minus. So OH minus is equal to Kw divided by the concentration of H3O plus. All I did is I rearranged my equation. Kw is 1.0 times 10 to the minus 14. And the concentration for H3O plus is 1.0 times 10 to the minus 5. This is given. So the concentration of the OH minus is 1.0 times 10 to the minus 9 molar. You guys, always the concentration is expressed in scientific notation. So always make sure that the concentration of both acids and bases, H plus or OH minus, is expressed in scientific notation. Okay? So I can see over here that if I want to compare the concentrations, I can see that the concentration of the base, look, you can easily see if your solution is acidic or basic by simply comparing the concentration. Or you can go ahead and calculate the pH. We'll do it both ways. But if you want to compare the concentration, just take a look. Concentration of the base is less than that of the acid. So you can easily see that your solution is acidic. So I can easily classify from the concentration that my solution is acidic. So it is acidic because the concentration of the H plus is larger than that of the OH minus. So you can do this, or if you want, you can go ahead and calculate the pH. So we can calculate the pH of the solution by simply using this equation. pH is minus log, this is log base 10, okay, in your calculator, multiplied by the concentration of the H plus in there. Guys, from your calculator, different calculators, they do have their own rules, but most of the calculators do this. Whenever you plug this equation up, this is what you need to do. So put the concentration of the H plus first, and then do the log, okay? So the concentration of H plus, then do the log. The answer for this one is going to be negative. So negative times negative, it's going to be positive. Your pH is always positive, always positive. So that is equal to minus log. We're going to substitute the H plus in there, which is 1.0 times 10 to the negative 5. The answer is going to be negative 5, and you already have a negative in front of the log. This is the negative. So negative times negative is positive. So your answer is positive. pHs are always positive, you guys. So this is going to be positive 5.00. And we always going to try to express this as a 3 significant figures. So pHs always try to express. So try to express or show the pH as, this is pH, as 3 significant figures. Let's have another example. This over here shows what you need to do to put it in a calculator. So calculate the pH of the solution with the concentration of H plus, so similar to the one above. We know that pH is equal to minus log concentration of H plus. So you just go ahead and you substitute the concentration of the H plus, which is 1.0 times 10 to the negative 9. All calculators, whenever you want to put this in the calculator, plug this number in the calculator, you should just type 1.0, and then there's an exponent or exponential factor in the calculator. So you do exponential and you put 9 negative. And then you do the log for it. The answer will be negative. You multiply it by negative, and your answer is going to be positive. So this one is going to be, the answer for that one is going to be minus 9. So your answer over here is going to be plus 9.00. So what does 9.00 mean over here? It means that your solution is basic. So this one is going to be basic. We did not mention up there. So see, here in this example, we did deduce that it is acidic, and we did the pH, and it was acidic as well. So your answers have to be matching each other. Okay, calculate the concentration of the OH minus for a solution with pH is equal to 4. Guys, these examples, they do cover all the types of questions that we might ask for the pH and the pOH calculation. So now they want the concentration of the OH minus. They gave you the pH. When they give you the pH, go ahead and calculate the concentration of H plus. And you already know the Kw and the relationship between Kw and the concentration of the H plus and the OH minus. So this is our layout for the problem. We are going to calculate the concentration of H plus. So the concentration of H plus now from the equation is 10 to the minus pH. Okay, so that is 10 to the power. There should be an option in your calculator of 10 to the power. So you put 10 and then you put to the power in there. The power of the pH, so 10 to the power pH, you already have that to be minus 4. Okay, so that is your concentration. So your concentration is equal to 1 times 10 to the negative 4 molar. This is the concentration of the H plus. Now, once you do the concentration of the H plus, we're going to go ahead and, because the question is they want the concentration of the OH minus, I know the relationship between Kw is equal to the concentration of H plus multiplied by the concentration of the OH minus, right? Okay, this is how we get the concentration of the OH minus. We already have Kw, we already have the concentration of H plus. So all what we need to do is just plug in the numbers. So concentration of the OH minus is equal to Kw divided by the concentration of H plus. Kw is 1.0 times 10 to the negative 14, and the H plus is 1.0 times 10 to the negative 4. So your answer here is 1.0 times 10 to the negative 10, and that is going to be molar, and that is the concentration of the OH minus. Let's do another example. Calculate the pH of the solution in which the concentration of the H plus is equal to that much. So it's a simple pH substitution in the actual equation. You already are given everything, so just put everything together. 3.6 times 10 to the minus 4, and that is equal to minus a 3.44. It's equal to positive 3.44. You guys, very important, pHs are always positive. Okay, another example there, same as before. So I know that the concentration of H plus is equal to 10 to the minus pH. Since I am given the pH of the solution, then in this case I can go ahead and substitute. It's 10 to the minus 5.92. Just put that in your calculator, and it's equal to 1.2 times 10 to the minus 6, and it is going to be molar. Always we measure the concentration units in molar or moles per liter. So acids undergo, of course, reactions, right? And it's not just acids and bases. So acids react with bases, and acids also, they do react with other compounds as well. Now we know that all acids, they taste sour, and they do produce H plus whenever they dissolve in water. This is why we call them an acidic solution. All acids, they do undergo other reactions other than acid-base reactions. So they do react with other compounds. And the type of reaction that they undergo is a double replacement reaction. Acids, they do undergo reactions with solid oxides, hydroxides, carbonates, and bicarbonates. And the reaction is going to be a double replacement reaction. So let's go ahead and write down the products for each one. Since it's the double replacement, then magnesium is going to couple with the chlorine, and hydrogen is going to couple with oxygen to make water, right? And then make sure that you balance your equation, please. So your equation over here is going to be magnesium chloride, and that is going to be aqueous. So you're going to make salt in there. So magnesium chloride is what? This is kind of like salt, because it's going to dissociate into its ions, plus water. Water is going to be liquid in there. So HCl reacts with metal oxide. So this is going to be the solid oxide there in order to produce magnesium chloride and water. If we want to draw the net ionic, before drawing the net ionic equation, we're going to go ahead and balance this equation, okay? And then draw the total ionic and then the net ionic. Maybe it's easier. So we're going to balance this. We have two chlorines, right? So we're going to go ahead and put 2 over there. And then we have 2 hydrogens on this side, oxygen, magnesium. It is balanced. You never draw the net ionic or the total ionic before you go ahead and you balance your equation. So once I balance my equation in there, remember, for the net ionic, I have to get rid of all the ions that are common between the reactants and the products. These are the spectator ions. So it will be helpful if I go ahead and draw the total ionic, okay, so that I can take into consideration every single ion that I have in there. So HCl, that is going to be H plus aqueous plus HCl minus aqueous. This is A plus Cl minus, I'm sorry. That's supposed to be a Cl minus aqueous in there. And the reason why HCl is aqueous, it's telling me that it is aqueous. So it's dissociating in there into H plus and Cl minus. plus MgO remains solid because it's a solid. It doesn't dissociate. You're going to end up getting MgCl2. So that is going to be an Mg2 plus aqueous. It's to the power 2 plus aqueous plus 2Cl minus aqueous, plus of course water, which is going to be liquid. Liquid stays liquid, solid stays solid. The ones that are aqueous are the ones that go ahead and dissociate into their ions in there. So what do I have as a common ion? As a common ion, I do have the Cl minus, and one more thing. When you dissociate this, just make sure that this is 2 and this is 2, just to follow the coefficient of the HCl, and your equation is balanced for the total ionic, so that you can take out the 2Cl, you can take out the 2Cl in there. Guys, pretty much this is it. So this is it. So now the net ionic is everything else that remains. And the net ionic now, it's going to be 2H plus aqueous. This is the net ionic, plus the MgO solid. Remember, we said that net ionic, it simply explains the solid in there, so it shows the solid and anything that was not dissociated. So you do have the remaining, which is Mg2 plus in there, aqueous, plus you do have water, which is going to be a liquid. So that is going to be the net ionic, and the spectator ion in this case is going to be the chlorine, because it's a common between reactants and products. So this is an example of solid oxide, okay? Solid oxides undergo reaction with acids, and your product is going to be salt plus water. Salt plus water. So this guy over here is going to be salt. Salt that dissociate into its individual ions. Metal hydroxides also react with acids. So this is the second type of reaction, goes also by double replacement, and this is the metal hydroxide. Reacts with acid, and the product is the same thing. It's going to be salt and water. So the salt is going to be the MgCl2. This is the salt. So you're going to end up getting MgCl2, and this is the salt, which is aqueous, plus water as well. So I do have H2O liquid. I need to balance the equation, you guys. So I know that HCl, I do have 2 chlorines in here, so I'm going to start by balancing the chlorine. And then after I balance the chlorine, I need to balance the hydrogen. I have 2 hydrogens here, 2 hydrogens there, so this is 4 hydrogens. So I need to balance the hydrogens on the other side to be 4 hydrogens as well. And this is going to be my balanced equation. After you draw your balanced equation, let's go ahead and draw the net ionic equation. You can draw the total ionic equation, but I can easily see that this one also is going to dissociate into its ions. So the Cl over here is going to cancel with the Cl up there, similar to the one on the top. So I'm not going to write it down. So my answer for the net ionic is 2H plus aqueous plus the Mg, the metal hydroxide, Mg2 solid. You can go to the solubility table of I believe it was a chapter number 6, probably 7, chapter number 7 maybe, or chapter number no, I think it is either chapter number 7 or chapter number 5 maybe. So go to your solubility. You can go to your solubility table from earlier chapter and figure out the solubility for metal hydroxides. You're going to see that magnesium hydroxides are always solids. They do not dissociate. And I'm going to end up getting my Mg2 plus aqueous. I took out my 2Cl minus, this is spectator ion, plus 2 water. And that is going to be the net ionic equation. Another reaction of acids is the reaction with carbonates. So solid oxide and hydroxide, they make salt and water. This is salt and water again. So for carbonates, carbonates, they dissociate into salts again. So you're going to make a salt in there, and you're going to make carbon dioxide probably and water from the carbonic acid. So let's go ahead and draw the product. So it's going to be magnesium chloride. That is going to be aqueous. So you still are going to form a salt in there. So salt is always formed whenever acids undergo chemical reaction, plus the leftover, which is the hydrogen carbonate. So it's going to be hydrogen carbonate in there. So that is going to be hydrogen carbonate is H2CO3. Why? Because the CO3 is 2 negative and the hydrogen is a positive. So we're just going to go ahead and crisscross those charges, and this is going to be H2CO3. Guys, hydrogen carbonate is very, very, very unstable. And because it's unstable, this one is going to dissociate. It's not going to stay as hydrogen carbonate, so it's going to dissociate into carbon dioxide and water. So you're going to end up getting carbon dioxide and water. Balancing the equation, you do have 2 chlorines, so this is going to be 2 chlorines in there. The total ionic, so this one is going to be the total ionic. It's going to be 2H plus, aqueous plus 2Cl minus, aqueous in there, plus MgCO3 solid. That is going to give you Mg2 plus aqueous plus 2Cl minus aqueous. And as we said, carbonic acid is going to dissociate into carbon dioxide and water. We're going to cancel the spectator ion. So this is going to be the spectator ion in there. So we're going to cancel that. And then the net ionic here is going to be 2H plus aqueous plus MgCO3 solid. That is going to give me Mg2 plus aqueous plus carbon dioxide plus water. Okay, just make sure that your equation is balanced. I do have 2HCl, that's right, and then I do have magnesium, I do have the CO3, so that is going to be my CO3 in there. I have my 3 oxygens, my 2 hydrogens, and my carbon. So everything is balanced. So here you go. This is the balanced chemical equation. This is going to be the net ionic equation for the reaction of HCl with metal carbonate. The last one is the reaction with the metal bicarbonate. We use the term bi whenever you have a hydrogen in there. So it's called metal bicarbonate. So here we have magnesium bicarbonate. I'm reacting HCl with magnesium bicarbonate. So again, I'm going to make salt. So again, I'm going to make salt in there. So the reaction is going to be HCl plus magnesium bicarbonate. This is a solid. I'm going to make MgCl2, which is a solid, plus 2 carbonic acids in there. So I'm going to end up getting 2 carbonic acids, just to balance the equation. Here you go. It's going to be 2 carbonic acid because since I do have over here the 2, so you're going to balance that. I have 4 hydrogens now. I have 2 chlorines, 1 magnesium. I have 2 carbons in there, and I do have 6 oxygens. So the carbonic acid, we know that carbonic acid dissociate into carbon dioxide and water, right? But because you do have 2 over there, then it's going to dissociate into 2 carbon dioxide, 2 CO2, and 2 water. So it's going to dissociate for both. So if I want to go ahead and draw the net ionic for this equation, it's going to be 2H plus aqueous plus Mg HCO3 solid. That is going to be Mg2 plus aqueous plus 2CO2 gas plus, of course, water is going to be a liquid.